Welcome back to lecture 25.3, where we're going to talk about superfluidity. The conclusion. All right, now, yeah, sure, continued. All right. So in 25.2, we talked about superfluid helium-4. We said basically what happens is it's a phase transition called Bose-Einstein condensation. It was actually the first BEC. It was discovered in I think 1939-ish, 1940s. It was really kind of nailed down after the war after 1945, but it was seen in the late 1930s. It was actually seen in 1908 by Kamerlingh Onnes when he liquefied helium. But it wasn't really understood until later to be this Bose-Einstein condensate. It was the first Bose-Einstein condensate, by the way. And it really is it's a phase transition where suddenly there's a macroscopic fraction, a non-negligible fraction of the quantum particles in their quantum ground state, which means they have this really long macroscopic wave function, which means that they kind of short the sample, right? So this is the physical property of superfluidity. So that's in helium-4. So electrons can pair up from these composite bosons out of these fermions and do the same thing. But now I want to ask, okay, can superfluid helium-3 become a superfluid? Can helium-3 become a superfluid? Obviously, the answer is going to be yes. But how do we do that? But also, I want to ask, how do we get to these temperatures? So remember that liquid helium, and when I say liquid helium, I say liquid helium-4. It liquefies at 4.2 Kelvin. Okay? So how can you get down to 4.2 Kelvin, first off? So you should know at least one way, but probably you should be able to guess two ways. So remember that we used throttling and the Lindy cycle, which was basically throttling with regenerative heat exchangers. That was how we liquefied helium-4. So these days we actually use a kind of refrigerator called a cryocooler. And this actually uses the Stirling cycle. So the Stirling cycle is actually kind of like the Carnot cycle. You have, you have isothermal expansion, which is a cooling cycle. You have isocores, so this is an isotherm, isocore, to drop the volume. You re-expand, you compress, you compress and then you heat. So you have isotherms where you're doing the expansion and contraction, and isocores where you're taking in heat and adding heat. So we use something called a closed cycle Stirling refrigerator. That's a cryocooler, where the working fluid is recycled. Okay. But let's imagine this gets me to 4.2 Kelvin, let's say. Can do a little bit better with these Stirling cycle refrigerators, but not much. So how do you get below 4.2 Kelvin? So you now have another tool in your toolbox to get to even lower temperatures, right? And that's what we talked about in lecture 24. We talked about the coexistence curve between a liquid and a gas. So remember, that was a pressure temperature phase diagram. And we had that the liquid and the gas. And we had that the pressure of vaporization was a temperature, function of temperature, was minus E, the latent heat of vaporization over RT. This was an exponential. Okay, so what we can do, you can see, is we can lower the pressure above a liquid. That is, you pump on the gas. And when you lower the pressure, you follow your coexistence curve down to a lower temperature. And so what you can really think of that is so remember our Clausius-Clapeyron equation, delta P, or dP over dt was delta S over delta V. And this was LV over TC V, TC delta V. I think this is, was that the temperature of vaporization? So along the liquid to gas coexistence curve, what happens when you lower the pressure is you can really think you're actually changing the entropy of the system. You can imagine actually taking the molecules out of the liquid, and as you sort of pull them into the gas phase, you actually have to have this latent heat of vaporization. So you're actually, by pulling these gas atoms out of the liquid and into the gas, you're actually pulling that latent heat with them, right? And you're decreasing the entropy of the system. And so you're decreasing the temperature. This is exactly what you do as a human being to regulate your body temperature, right? You push liquid onto your skin, which then when it evaporates, carries that latent heat with it, causing you to decrease in temperature. So that's sweating, right? So just like you can drive this process faster by pumping on it, we fan ourselves to force that evaporation of the liquid on our skin and cause ourselves to cool. It's exactly the same process. So now you actually take an entire course on thermodynamics and you can understand sweating. Okay, so it's exactly this process. So with liquid helium-4, the problem though is that this curve is exponential. And it really probably would be better if I showed it really kind of as an exponential, where it looks something like that, right? And you can see down here, this is very flat, right? So this very flat part of the exponential means that the vapor pressure is dropping really fast. And so what that means is that this cooling system loses effectivity. Loses its effectiveness. That's what I wanted to say. It loses its effectiveness. And for liquid helium, it loses that effectiveness about 1 Kelvin. Okay, one other thing I want to point out about this, though, is actually, if you're along this coexistence curve, right? Along the coexistence curve, the pressure is an indicator of the temperature. What do we call this? We call this a thermometer. So this is called a vapor pressure thermometer. And this is a part of the definition of temperature, right? So this goes all the way back to the initial lectures where we were talking about thermometry and the International Temperature Scale. So this is a part of ITS 90 and the PLTS 2000. All right. Now, if I am a researcher looking for superfluid helium-3, I can look down to about 1 Kelvin. I actually, that's low enough that I can get my phase transition to superfluid helium-4, but if I look at helium-3, I do not yet get a phase transition. So I need to cool further in my journey to look for this phase transition. So how do I do it? I want you to think of an idea. Pause if you need to and stop and think. What can I do? So what we're going to do is we're going to switch isotopes. So if you switch to helium-3, it's lighter, so it has a higher vapor pressure. And it liquefies at 3.2 Kelvin. And when you can pump on it, because of that lighter mass, higher vapor pressure, you can actually pump and cool to approximately 300 millikelvin. If you do that and you look for a superfluid phase transition, you still don't find it. Okay, so you need to cool further. And when you cool further, you're stuck, right? You have no other isotopes, right? How are you going to ever get below 300 millikelvin? Well, what we need is a revolution. We need a new kind of refrigerator. So this new kind of refrigerator was invented in 1962 by H. London. There's two Londons and they're brothers. There's Fritz London and I'm based on his name, Height London. That's wrong. H. London, 1962. So he invented what we now call the dilution refrigerator. Okay, so actually, I hope to give a lab tour, a virtual lab tour. I'll show you pumped helium-4 refrigerators. I'll show you a pumped helium-3 refrigerator, and I'll show you dilution refrigerators. Because we use all these techniques, and we use those kind of Stirling cryocoolers in my lab. I'll show you all of these various aspects. So, of the dilution refrigerator, instead of using the latent heat of vaporization, it uses the latent heat of mixing. And it uses the latent heat of mixing the two isotopes of helium. Okay, so to understand this next step, to understand the dilution refrigerator, we actually have to look at the phase diagram, okay, of the mixing of two isotopes of helium. Okay, so I'm going to draw this as a box. So on this axis is going to be temperature, And on this is going to be the concentration of helium-3. Okay? So this is going to be, let's say, 100%, and this is going to be 0%. There are two isotopes, and I can just mix them. So this is thinking about a mixture of these two isotopes. Okay, so I'm going to start up here at 2.17 Kelvin. Let's make that a little bit bigger. So this is going to be my temperature axis, and this is going to be 2.17 Kelvin. So this is going to be when we have pure helium-4, we have a superfluid. And above it is a normal fluid. But actually, as we mix helium-3 in, it actually decreases the superfluid transition, so it goes down. Okay? And it goes down, and it goes down, and it goes down until a particular temperature. So this temperature is going to be 0.87 Kelvin, in which the two phases of helium are no longer miscible. They actually phase separate. So even though they're two isotopes, they, at low enough temperature, it's actually this phase transition is again determined by the third law. There's too much heat capacity in all that helium-3. And so what happens is you actually get, let's see if I can draw that nicely. Two domes. Let's see if I can do it. I'm going to slightly back up. Okay, that's close. Okay, so this is a particular concentration, which is 6.6 or 6.7%. And what happens is if this is called the two-phase region. Okay, what does that mean? It means that if I were to be, for example, let's say I had a concentration of 30%, okay? So this is roughly a kind of roughly special number. Let's say I imagine it had 30%, and I were at this temperature. I'm not allowed to be in this part of the phase diagram. Instead, I actually have some helium that's this phase and some that's this phase. Okay? And so what are those two phases? So they're actually so there's a region that's 100% helium-3 and one region that's about 6% helium-3 and helium-4. Okay? So in the two-phase region, below a particular temperature, it's called the separation temperature. We have two phases. One is pure helium-3, right? It's basically 100% helium-3, and one that is called dilute helium-3 and helium-4 at about 6.6 or 6.7%. So if I imagine a vessel at high temperatures, it's mixed, but at low temperatures, they'll actually phase separate, and we have helium-3 that's pure, and then we have helium-4 with some helium-3 in it. 6% helium-3 in helium-4. Right, helium-4 is heavier, so it's on the bottom. And now, this understanding of the phase diagram is what allowed London to make the prediction for a dilution refrigerator. So what happens in a dilution refrigerator is you actually, it's weird, but you actually pump on the bottom. How do I want to show this? Let's show it like this. I'm going to have a tube that goes to the bottom of my liquid. And I'm going to pump on that. So again, helium-3 is lighter, so has higher vapor pressure. Okay, so you actually preferentially pump the helium-3 out. Now what happens? Well, I'm still in this region. I've got this pure phase. But my system really wants to have 6% of helium-3. It doesn't want to be over here. It wants to be along this line. You really want to be in these two phases. So what happens is some of the helium-3 moves into this phase. Okay. So as I pump out helium-3, so let's do it in green because I think of helium-3 as green. Okay, so helium-3 is pumped out. And as a result, to keep this 6%, helium-3 moves across the phase boundary. And it's that mixing or dilution which has a latent heat associated with it. And you can sort of think about this as going from a liquid helium-3 to a gas of helium-3, right? There's a gas of helium-3 that's sitting in this helium-4 superfluid matrix. So it's sort of like this evaporative cooling, this pumping on it, but in fact it's really dilution. It's mixing. And the cool thing about this is there's always around 6% of helium-3, and so you don't have this exponential vapor pressure that you had in pumping on helium-3 or helium-4 alone. You always have this finite concentration. You have that finite amount of helium-3. So when you keep pumping, you just keep returning. So what we actually do is this goes to room temperature. It gets cleaned of any impurities, and then it gets put back into this as a closed system. So we have pumps, and then we have obviously quite a bit of heat exchangers so that you don't heat things up. So this is how a dilution refrigerator works. So dilution refrigerators, the world record is around 2 millikelvin. Our fridges, one of them has gotten to 6 millikelvin and the other to 7.5 millikelvin. Okay? And if you get to 6 millikelvin or 7 millikelvin, you look for superfluid helium-3 and you still don't see it. Okay? You still don't find superfluid helium-3. So you need one more tool. You need one more refrigeration technique. And I'm going to tell you about it even though we don't quite have the tools yet. You really think about them more in terms of StatMac. But the final tool, the final refrigeration, is called adiabatic nuclear demagnetization. Demagnetization. And this I can actually link up to the base of a dilution refrigerator and allow me one further stage of cooling. And very briefly, the way adiabatic nuclear demagnetization works is if you actually look at the temperature dependence of the entropy for a material with a nuclear susceptibility. So this is a magnetic susceptibility of the nuclei. For so we actually use copper in our system. And if you look at calculate the entropy at high temperatures, it's constant. And of course, to satisfy the third law, it goes to 0 as T goes to 0. That's in zero magnetic field. But if you actually start at a higher magnetic field, at the same temperature, the entropy will be lower. This guy has to go eventually to the same state out here, some very high temperature. That's supposed to be continuous. But you can imagine at some particular temperature, if I have a higher magnetic field, I have lower entropy. And so what we do is we actually have a system that is, say, at zero magnetic field, we magnetize it. When we do that, it actually heats up a whole bunch, but we can actually cool it back down. So we can actually heat up and cool back down. And then, if you isolate the system from the rest of the world, so that dq is 0, if dq equals 0, then ds equals 0, all right, because S is Q is TdS. So if we have 0 heat coming into the system, then if we lower the magnetic field again, we actually have to end up on this curve, but entropy can't change, right? And if we look at what happens there, we've actually ended ourselves at a lower temperature than when we started. So this is a process in which, unlike most of these processes, when you have a latent heat or a latent heat of mixing, a latent heat of vaporization, you're actually pulling entropy out of the system. This is actually a constant entropy process, but you hop down to a lower entropy temperature curve. And so you're at a lower temperature. And so with this, you should be able to get down to, say, hundreds of microkelvin. So in my group, we have achieved 700 microkelvin. We should be able to get to more like 400 microkelvin. But there's some work to be done there. But at these temperatures, you can actually find, finally, that superfluid helium-3 we were looking for. And so the helium-3 phase diagram, pressure versus temperature, looks like the following. So at some very high temperature, around 300 millikelvin. So this is the solid, this is the liquid. There's this funny minimum in the melting curve. This is 29 bar that occurs at, 29.3. This is at 35 bar. So you can already see there's something really interesting about this. It stays a liquid all the way to 0 temperature. It doesn't solidify. This is because that quantum mechanical 0-point energy is actually large enough to keep the atoms moving enough that they stay a liquid. This is exactly counter to what most people think they know about absolute zeros, that all motion stops. You know, a liquid is defined by the motion of atoms. So here in helium-3, and actually helium-4 does it too, they don't liquefy all the way towards absolute zero because of quantum mechanical energy, right? So it's patently false that all motion stops at absolute zero. You can have liquids as you approach absolute zero. Finally, at around 2.49 millikelvin, and this is down around 900 microkelvin at lowest temperatures, lowest pressures, you actually enter into the superfluid. And it turns out there's not one superfluid, there's actually two superfluids. This is called the B phase, and this is called the A phase. And so the way superfluidity was discovered in 1971, 1972 by Osheroff, Richardson, and Lee is they were actually following this liquid-solid coexistence curve, and they saw little jumps and kinks in this curve, right? And that's because this one is a second-order phase transition, and this one is a first. So actually, when they had a fixed volume and they're following this melting curve, they actually saw a change in the heat capacity because it was a second-order phase transition. And here, they actually saw a little discontinuity because the entropy and the volume have a discontinuity, and that's a first-order phase transition. So they were able to see those kinks and jumps in the pressure temperature, the pressure as they follow the pressure temperature coexistence curve. And so actually, this is something that we study actively in my group, and we're looking for some new superfluid phases. And actually, I think what I'll do is I'll post a link to the colloquium I gave at the beginning of the year, and that tells you a little bit more about some of the stuff we're actively doing in my group. So you can watch that, and then we'll actually, I'll post that at the same time as this one. And then next time, I'll go and I'll give you a lab tour, okay? All right, and with that, we have finished the material for the course. Thanks all.